breakthrough.
Programmes on BBC One continue in a moment with Tomorrow's World. Then at 7:20, Top of the Pops includes music from Lena Lovitch, Bad Manners, Kim Wilde and Shakin' Stevens. Then an hour of comedy begins at 8 o'clock with Heidi High.
Pixie, under the stars! Peggy!
Followed at 8:30 by Sorry with Ronnie Corbett.
Bodybuilder, are we, sir?
Bodybuilder, yes.
Got a long way to go, haven't we, sir?
At 9:25, Leicester, a profile of one of Britain's best-known sportsmen, narrated by Tom Conti.
Whenever there was a chance of a good ride, Piggott was there, ever searching for that next classic winner.
At 10:15, facing Question Time are Dick Taverne, Nicky Harrison, Gerald Kaufman and Douglas Hurd. And Kojak at 11:20 rounds off tonight's programmes on BBC One.
And now, a look ahead to Tomorrow's World.
When a lumberjack shows off his skill with an axe, he knows just where the blow will land. It's a lot more fun than chopping firewood. See, the problem is, unless you split the wood first time, the axe gets stuck. So, maybe here's a solution. Now, the log-splitting power of this new design lies in the addition of two metal levers set into the head of a conventional axe. Each lever rotates through 90 degrees on a pivot, and it's spring-loaded in the closed position. So, as the blade enters the top of the log, the levers swing out, transforming the downward momentum of the blow into an outward force to wrench the wood apart. All of that is theory. What you're about to see is the real thing. Ah! Good grief, it works.
Which look quite ordinary, often involve sophisticated technology today. This yellow tablet, for example, was designed to dissolve slowly once it's inside the body, steadily releasing its drug throughout a 12-hour day. It starts to erode away as the tablet passes through the digestive system. Here it's in the stomach. So the drug can be carried away by the bloodstream to different parts of the body where it's needed. But to be sure that drugs are released at the right time, doctors need to know the precise rate at which the tablet dissolves. But investigating the way tablets behave in the body is not without its problems. Those pictures you've just seen were taken using this instrument, a gastroscope. And it's this part which actually has to go down the patient's throat until it reaches the stomach. A difficult business, and it doesn't even tell the scientists how fast the drug dissolves. In the past, they even tied tablets to pieces of thread. The patient swallowed it, and then it was pulled out from time to time to check how much of the tablet had dissolved. Or you can do laboratory tests, putting tablets into pieces of equipment like this and watching how fast it dissolves. Although you can't guarantee that tablets will behave naturally in the laboratory. But now there is an easier way of studying tablets in the body using a trick from nuclear medicine here at Nottingham University. What they do is they radioactively label part of the drug, mix it with larger quantities of the drug, add the base material of the tablet, compress the mixture, so you end up with a radioactive tablet. It's as safe as having an X-ray, and it can be followed through the digestive system. That's done using a gamma camera, which has a sodium iodide crystal behind here to pick up the radiation. That's converted into electrical signals, which are shown on the monitor. All that's needed now is for me to swallow the tablet. But first of all, I'll just prove that it is radioactive. There's certainly no doubt about that. Right, here goes. Now I have to take a liquid containing a different radioactive marker. That outlines the stomach and the rest of the alimentary canal. Already you can see on the monitor the white tablet at the bottom of the stomach, and the blue is the radioactive liquid arriving and outlining the stomach's area. To get an accurate picture of just how fast the tablet's dissolving, the computer can box it in and calculate its area as it moves through the body. By using radioactive liquids and tablets to pinpoint where and when drugs are released, doctors are already planning more sophisticated ideas for both new and very common medicines. That could include an improved version of these. They're a new type of aspirin with a hard outer coating that won't dissolve in the acid environment of the stomach, where aspirin can cause bleeding, but will only dissolve safely in the intestine. These are a typical example of new formulations of old medicines that will be tested by this equipment and will lead to better treatments for us all.
In this week's Radio Times, you may have seen an article on tomorrow's world and a deceptively simple photo.
Which only takes a moment to look at, but is in fact a time-consuming piece of work.
So today we're going to keep our promise to show what went into making it.
And why it took so long to complete. Of course, the picture you're seeing now is made electronically and transmitted live, but its twin, printed in Radio Times, actually went to press 4 weeks ago. As the presses roll, the colour pages are printed onto vast lengths of paper. At full speed, this process is incredibly fast. Passing each page over the series of cylinders which build up the full colour image takes a matter of seconds. Preparing the colour pictures to produce that image takes much longer, so all decisions about these colour pages have to be made 5 weeks before printing starts. But now, technology is being developed which could cut that timescale drastically. The idea is to employ electronics in the translation of these, the original photographs, into the composite image on the magazine page, a process which at the moment involves special photographic films, films which are used to produce the printing cylinder. But an awful lot of them are needed. Films are employed to reduce the size or alter the shape of the image, to marry one image on top of the other, to ensure the right proportion of blue, yellow, red and black in the magazine page so that the colours represented there are true recreations of the colours in the original photographs. Films are also needed for retouching, for correcting minor blemishes, for modifying small areas, and the list by no means ends there. But soon, all these films could be replaced by magnetic memories. At the heart of the new system is a scanner, a drum on which each photograph is rotated, allowing a record to be made of the brightness and colour of every point on the picture. Once this information has been fed into the computer's memory, the press of a button can call up the original image on a monitor screen, and the operator can manipulate that information, even replacing bits, like Judith's fingers, that get lost in the shuffle. Data from one memory can be drawn out and superimposed on information from another. But even publishers who already use this layout technique now have to resort to traditional photographic film, because the hand of the artist is still needed for the final beautification, moving hairlines, altering necklines. Using a fine brush, and in this case a small quantity of bleach, a less than perfect set of teeth can be whitened. Not that the eye can see the result here. Even the artist will only know if she's got it right when she sees a printed proof. Now, even the most delicate of retouching can be achieved electronically in seconds. And what's more, if I don't like the changes I'm making, I can alter them instantly, because all the while I can see what I'm achieving on a colour television screen. So, what about that smile? Well, let me start by magnifying the image and filling the screen with Rod's face. Now, it took the expert doing it conventionally 10 minutes to brush up the simper into something presentable. Let me introduce a cursor across into our image and attempt to do in seconds more or less the same thing. Now, what I'm doing now is delineating the area that I want to alter electronically. Right, all the way around the teeth. Now, I can alter the intensity of the teeth, quite independent of everything else in the picture, with some amazing results. The same technique can suggest some extravagant makeup for Judith's eyes and catch a special twinkle in Kieran's. Watch the eye on the right carefully. I can even give Sue a useful third hand. Just a few examples of what this prototype electronic system is capable of doing. And of course, the computer now contains all the information for producing the actual printing cylinder. So, why not take this process one stage further? Link it to a laser, and we have the basis of an entirely new system for engraving cylinders. The carbon dioxide laser operates just as a cutting tool in a lathe. Controlled from the magnetic memory, its power is altered to burn a pattern of grooves in a plastic-coated cylinder. Within a few minutes, the image for the page emerges. The cylinder is ready for printing. How long it will be before this system becomes commonplace in the printing industry is bound to be a subject for long negotiation and debate. But here it is, the first full-color, all-electronic page for the Radio Times. Now, the similar page you have in the magazine at home took several weeks to prepare for the printers. This one was ready in less than half a day.
Victorian women of beauty and influence all had one thing in common: a smooth, lily-white skin. So an exotic parasol, to keep off the sun, was an essential part of their exotic summer wardrobes. How things have changed. Today, far from a delicate complexion being the indication of wealth and sensuality, an all-year tan is now the ultimate in status symbols. But getting that ideal tan can be dangerous. We now know, for example, that there's a connection between skin cancer and long exposure to the sun. So now it's back to the parasol again. But this time, not a parasol to keep you white, but to help you tan more safely by cutting out the dangerous band of ultraviolet light called UVB, which burns and causes skin cancer, but allowing through UVA, which is safer provided you don't overdo it. So we decided to test the material using a machine called a spectrophotometer. Light from a lamp inside this section is passed through the sample here. The light scans across the spectrum, and this plotter records how much of each band gets through the material. You can see from the graph that we've just made on the machine that virtually no UVB gets through, and it starts to allow UVA light through here. So it's not surprising that this parasol has proved to be safe in tests carried out by the Institute of Dermatology. But some worshippers will pay a price for that safety, because the amount of UVA light getting through here is so low, it's been estimated that even at the height of summer, it could take up to 100 hours to get a tan under this parasol. So perhaps the sooner we go back to pale Victorian standards of beauty, the better.
Windscale in Cumbria. the home of Britain's nuclear reprocessing. Shortly before 11 a.m. on 26th September 1973, there'd been a leak of radioactive gas. It was from this building, an experimental plant for reprocessing one kind of spent fuel, oxide fuel. It was closed immediately, and 35 of these men's colleagues had radioactive contamination. The building to this day is closed. Yet the Japanese and other nations are constantly sending us their oxide waste for reprocessing. And under contract, we've got to accept it. All we can do is take it to Windscale for stockpiling. But on this site at Windscale, they're going to build a new plant for reprocessing oxide fuel. And to ensure that it's safer than the last, they've been researching into the cause of the 1973 leak. The problem there arose in the first step of reprocessing, where spent fuel rods are dissolved in nitric acid. The snag is that these alloys form. They're radioactive wastes which are insoluble in the acid, and that can lead to problems later on. A suspension forms which can affect the next stage of reprocessing, and that's probably what happened that morning at Windscale. The solids accumulated and then reacted with the acids, giving off radioactive gases which eventually leaked into the atmosphere. So it's essential to separate insoluble radioactive waste from dissolved spent fuel if reprocessing is to continue successfully. And up to now, that's not been easy. But remembering that the insoluble alloys are weakly magnetic, British Nuclear Fuels decided to try something here at Winfrith in Dorset. Using this magnetic powder, they built an experimental model to take solids out of a mixture. Over here is a suspension of the powder, and it goes through a system of tubes ending up in a very narrow glass tube. You can just see it running vertically, right in the centre. The idea is to take the solids out of the mixture using these powerful magnets on either side. When the main magnet is switched on, the magnetic effect is concentrated into an iron wire running down the middle of the vertical glass tube. As the mixture flows through, the black powder is attracted to the iron wire and so separated from the solution. The same would happen, they reasoned, with the magnetic nuclear wastes. And they would stay there until the main magnet is switched off. The wire would cease to be magnetic, and the radioactive waste could simply be flushed through and collected separately. After the success of this model, they built a larger prototype, using gold-plated ball bearings in place of the thin iron wire. To represent the nuclear waste, they used green chromium oxide in suspension. It's also weakly magnetic, just like the radioactive waste they hoped to separate out. To test it, the magnet is switched on, and the chromium oxide allowed to pass through the gold ball bearings. If it works, the liquid at the bottom should be completely clear. The process is so efficient that the end result is as pure as drinking water. Or so they say. Well, it looks all right. Even smells quite clean. And it tastes like drinking water. As in the smaller model, when the magnet is switched off, the solids can easily be separated out without anybody coming into contact with radioactive waste. The results from the prototype have been so encouraging that the plan now is to build a full-scale unit, 7 times this size, at Windscale's new oxide reprocessing plant. It's early days yet, but if all goes according to plan, the leak which happened at this plant in 1973 shouldn't ever happen again.
Are you one of the lucky people who bought a new car recently, or one of the unlucky ones? Because do you know where your car was stored after leaving the factory? Was it, for instance, here at Dover? Or maybe it was one of these at Poole? Was it in a field of grass at Radlett Aerodrome? Or was it up to its vitals in water at Southampton Docks? These pictures are just a selection from next month's Car magazine, which claims that there are around 450,000 unsold cars stockpiled all around the country. Of course, most new cars have anti-corrosion treatment and a special protective wax coating because it's normal to stockpile cars for a few weeks. But can that protect a car from this sort of treatment? Would you pay £4,500 for a car if you knew that it had been kept like this? Look at where the water level comes on this one, all the way up to the middle of the hubcap. Now, what harm could that do? Well, the AA's chief engineer told us that the whole brake system may need reconditioning. The drive assembly and transmission could be affected, the lower part of the exhaust system could begin to rust, water could seep past the seals and shorten the life of electrical components. Some damage might not show until well after the warranty period has expired. Well, all right, this car is an exceptional case, and in fact, this site was abandoned a few days ago. But the problem of long-term storage of cars in unsuitable places is one for the whole industry, as well as a consumer. The AA told us that no car should be kept under conditions where water can collect. Yet thousands of cars from many of the major car manufacturers have been kept for months on end on grass, in salt spray atmospheres, even in marshy conditions. Of course, all cars are checked over before they reach the showroom, but even the dealer might not know how old a car is or the dreadful conditions it's been kept in. So, as the stockpile increases and the demand for cars falls, what can we, the consumers, do? Well, the advice from the AA is check for dampness, check for rust. Our advice is, if you're not sure, get an expert to look at it. In other words, treat your potential new car just like a second-hand one. Mike.
Well, after that, let's look forward to Easter, which this year falls on the first Sunday after the first full moon after the vernal equinox. We can be certain of that, because it always does. But the date on which that occurs once taxed mathematicians sorely. In fact, centuries ago, a formula was derived to check the date of Easter each year without having to resort to the almanac. And that formula can be expressed like this. A numerical value is given to each of the letters spelling Easter. Wow. But fear not, Tomorrow's World and a calculator will help you through. In fact, capital E to start the letter doesn't need a calculator at all, does it? Because it says the year, take away 1900, answer 81. So let's put that up on this frame over here and move on to the second line, because we'll see that each of the answers is now dependent on the year. A, for instance, is the remainder left when you divide big E by 19. I think it's calculator time. 19 times 4, for the sake of argument, is 76. 81 take away 76, remainder 5. That goes in for A. On we go to S, which is 7A. That's 35 plus 1, 36, divided by 19, ignoring the fractions. 19, just in case you don't believe me, by 2 is 38, which is more than 36. So in this case, for 1981, the answer to S is 1. And on we would go. You see why it was developed centuries ago. T for 81 has a 0 value. E comes to 20, and R ends up at 6. Now, where's that got us? Well, look at our original formula. Easter is in any year 25, take away T, take away R. So in this case of 1981, it is 25, take away 0, which is 25, take away R, which is 6. The answer is 19. Check your diaries if you like, but this year Easter falls on the 19th of April. What you say would have happened if the total had come out negative? Well, the baseline for this formula is 31st of March. Positive 19 is 19 days into April. A negative answer would be so many days back into March. It works for any year. But all you aficionados of the electronic calculator will be saying, that is an awfully tortuous way of going about it. Isn't there anything quicker? Well, yes, there is. This is the very latest in programmable calculators. And spread round about it are just a few of the hundreds of programs it can deal with. Computer codes, today's complicated formulae. Let's look at this page, which is actually concerned with religious holidays. One quick trip across the barcodes with the wand will program this new unit with all the information it needs to carry out the calculation we've just looked at, and many more. Now, let's put this in just the right angle for you to be able to share the excitement at home. There's the display. It says, what's the year? 1981.
What's the holiday? Easter we're looking for. Remember how long it took to do this the last time? It thinks, it confirms it's Easter, and in 1981, lo and behold, April the 19th is the date. So the machine and I and the formula of the ancients all agree. We'll be back, of course, long before Easter, 7 days from now. Until then, good night to you.